So now let me summarize again. In order to implement the first version of the multiplication in MIP32, I need the following 1, 2, 3, 4, 5 hardware components. They include 3 registers to contain multiplicand, multiplier, and product, respectively. The register to contain the multiplicand should be 64 bits because I need to make sure when my multiplicand register shift to the left by 1 bit at each iteration, there's no meaningful bits will be lost. Okay, therefore, in order to initialize this multiplicand register, I need to initialize that to put out the original multiplicand on the right half of the register, and the left half will be all zeros. And the multiplier register is 32 bits because all I care is the least significant bit after they do the shift. And the product needs 64 bits because 32 plus 32 will be 64. That is already identified here, okay? And then because I need to do the addition between two 64-bit value, I need to make sure my ALU can support 64-bit addition. Besides 3 registers and 1 arithmetic logic unit operation, I need another brain which tell when the register will do shift, what operation ALU or what functionality ALU need to complete, and what kind of or when they will implement this operation. In order to do that, I need this control unit, which is the brain, to send the commands. And based on what they send the command? Based on the least significant bit of my multiplier. That's why you can see this arrow here. Okay? And then you can see here is a summarized step. Basically, you can see multiplicand and product will be 64-bit. Multiplicands are loaded to the right half of my multiplicand register as initial steps. And the rightmost bits of the multiplier will be shifted out to control whether or to send the commands to the control unit to decide whether this addition will be used to update this product. Okay, and also the control unit will decide when this will be shifted and so on. And ALU implement addition, right? And also will be use that to update product. And if you look at the, go back to this example, okay? Oh, let's just repeat this algorithm one more time, and then we'll go back to this example. So basically, I always look at the least significant bit of multiplier. If it's a 0, I do nothing. If it's 1, I will do the addition between the product and the multiplicand. And then I will shift the multiplicand to the register to the left by 1 bit. And then I will shift the multiplier register to the right by 1 bit. And then I will repeat 32 times because here I try to implement 32-bit I implement the multiplication in MIP32. Okay, so now let's look at this example. Here I try to implement the multiplication between 2 and 3. Okay, this is decimal number. If we convert to binary numbers, 0010 and 0011. Here is the assumption is my hardware support 4-bit multiplication, okay, rather than 32-bit. Just this is no special meaning. It's just try to simplify our demonstration. Okay, so here, if assume you have multiplier, multiplicand, and multiplier, one is a 4-bit, another is 4-bit too. So how many products you need to have? 4 plus 4 need 8 bits, right? If we look at here, basically now this multiplicand should be 4 times 2 is 8 bits, and the product is 8 bits, and the multiplier register is 4 bits. And then this ALU here will be 8 bits, right? And then I will put, you can see here, I will put my multiplier here, just 4 bits for the initialized steps. And then my multiplicand will be 8 bits. I will, in the initial step, I will put this original value to the right half of my multiplicand register. And then the product will initialize all zeros. And then will, based on the least significant bit of multiplier is 1 or 0, decide whether I implement addition or not. But this one, the least significant is 1. Therefore, I implement addition. Addition of what? Addition between the multiplicand and product. Therefore, you can see I will add multiplicand to the product, and using that addition value to update the product, which is shown as here. After that, I will do two shifts. One is shift the multiplicand register to the left by 1 bit, shift the multiplier register to the right by 1 bit. You can see multiplicand to the left by 1 bit, right? So you can compare these two. Basically, I shift this one to the left by 1 bit, will show here. And the second is a multiplier to the right by 1 bit, right? You shift this one to the right by 1 bit. Basically, you lose this least significant bit, which is shown here. Okay, now the first step finished. And then I will continue to check the least significant bit of the multiplier is 1 or 0. It is 1. I will do the addition. Similarly, using this multiplicand to add to the original product and using this addition to update product, which is shown as here. Okay? And then I will continue to do two shifts. Shift the multiplicand register to the left by 1 bit. Okay, which is shown here, right? And to shift the multiplier register to the right by 1 bit. Okay? After that, I will finish the second step, second iteration, and then continue with the third iteration, continue to check the least significant bit is 0 or 1. 0. I will not do any addition or other operation, so I just copy all the original values, the values achieved from last iteration, and then continue to do two shifts. Shift the multiplicand register to the left by 1 bit, shift the multiplier register to the right by 1 bit. After doing that, I will finish the third iteration, continue with the fourth iteration. Again, check the least significant bit of multiplier, whether it's 0 or 1. Here is 0. Therefore, I do not need to do any operation, and then I only need to do two shifts. Shift the multiplicand to the left by 1 bit to shift the multiplier to the right by 1 bit. Because I totally need to do 4 bits multiplication, I need 4 iterations. Okay? So if here is 8 bits multiplication, I will need to do 8 iterations. I hope this is clear. So now the question comes is, this is very straightforward, but there is some room we potentially can improve the performance. That is how we get the second version, we call the refined version of the multiplication hardware. So let's see whether there's some room we can improve, or what is the room we can improve. You can see here, in each iteration, I need to do 2 shifts, right? So if somehow I can reduce this 2 shift into 1 shift, okay? Or we say, that is one way we can improve. Another way is if I can, still do shifts, still do 2 shifts. The only thing is I will not shift the multiplicand. That is also good. Let me say one more time. There are 2 ways we can improve. One is reduce 2 shifts into 1 shift. Another is try to stop or avoid shifting multiplicand. Both of them can improve the hardware design. Why? If I reduce from 2 shifts to 1 shift, basically I save the overall time required to implement the multiplication. This is first. Second, if I avoid to do the multiplicand shift, then I potentially can only need, for example, this example, I only need 4 bits register to contain the multiplicand instead of 8 bits. In that way, I can reduce the requirement of the hardware resources, right? So for the first way to improve, actually we get the final version, or called the optimum version, or called third version of the multiplication hardware. For the second way we just talked, to improve the performance, we can get the refined version of the multiplication hardware. In today's class, we focus on refined version. In other words, we try to avoid shifting the multiplicand register so that I can reduce the number of bits required by the multiplicand register. How we can do that? Let's look at here, okay? Let's say I don't want to shift the multiplicand, okay? But I still need to make sure, all this aligned will be achieved. How we can do that? What is aligned? Aligned means the relative movement between the multiplicand and product, right? So if I say I don't want to shift the multiplicand register, but I still want to maintain or remain the relative movement between the multiplicand and the product register, what I need to do? I want to pause here to think about it. The one straightforward way to do that is instead of implement the shift left logic for multiplicand register, I can do the shift right logic or operation for the product register. Say one more time, the goal I want to achieve is not shifting this multiplicand register to the left, but I still want to keep the alignment this way. The alignment refers to the relative movement between the multiplicand and product registers. So in that, if I want to remain this without shift this one, the only way we can do is shift the product and shift to the right. That is how we get the refined version of multiplicand hardware. Basically, instead of shifting multiplicand registers to the left by 1 bit, I will shift the products to the right by 1 bit. By doing so, I do not need to give the multiplicand registers additional 32 bits room to avoid losing the important bits during the shift, because here is no shift anymore. Therefore, if I want to implement 32-bit multiplication in the MIPS32, all I need is a 32-bit multiplicand registers. Okay? So, and then the product, we still need 64 bits. But here, because I only need 32-bit multiplicand and add with part of the products, so here the ALU operation, I only need 32 bits. Okay, so what I really do is as following. In the initialization, I will initialize, the multiplicand still is a multiplier is still 32-bit, multiplicand here is 32 bits. So I just reinitialize whatever multiplicand I have to this register. And then the product still is 64 bits, okay? And then I will, if the least significant bit of the multiplier is 1, I will add this multiplicand, which is 32-bit, with the left half of the product. So that means I actually do is a 32-bit addition. Therefore, my ALU only need to either they support 32-bit addition. Okay, and then I will shift the product to the right by 1 bit. Of course, the multiplier still need to shift to the right by 1 bit, which is you get here. You can see I will check whether my multiplier, the least significant bit, is 1 or 0. If it's 1, I will add my multiplicand to the left half of the product, and then update the original value of product register by using this addition. And then I will, if it's a 0, right, least significant 0, I do not need to do any operation. And then I will shift the product register to the right by 1 bit, and then continue shift the multiplier to the right by 1 bit, and then repeat 32 times. Okay, if I look at this example here, just to save some time, instead of I doing the 32-bit multiplication, I do 4-bit multiplication. Okay, therefore, instead of implement 32 iterations, I will do 4 iterations. Okay, so you can see I initialize the multiplier with 0011 4-bit, initialize the multiplicand register 0010 4-bits, I initialize products all zeros. And then I will base on the least significant bit. Here is 1, therefore I will add my multiplicand to the left half of the product. Okay, and then I will shift my product to the right by 1 bit. You can see here, right? Shift the right by 1 bit, and shift the multiplier to the right by 1 bit. You can see here, shift the right by 1 bit. After that, I finish my first iteration. Similarly, continue to check whether the least significant bit of my multiplier is a 0 or 1. Here is 1. Therefore, I will add my multiplicand to the left half of the product. And then I will shift my product to the right by 1 bit, shift my multiplier to the right by 1 bit. And then the second iteration finished. And then we'll check the least significant bit of multiplier again. Is 0. I do not do any operation in the third iteration. The only thing is the shifts. Okay, and then I will finish the third iteration. I will check the least significant bit, 0. Do not do anything in the any operation in the fourth iteration except the shifts. After that, because I do 4-bit multiplication, I need 4 iterations, and the final results will give me the product. I hope this is clear to you.